Okay, we started talking about interface shear, and I'm not going to go through all the details because we've already talked about this and done this once. But we derived this. We re-derived this concept that when you put shear and moment on something, that you're going to create internal shear, and create internal forces inside the member. You have to, because as you go from left to right here, your moment's going to get larger from on one side than the other, and the only way that resultant from this and the resultant from this is going to be larger. The only way they can balance and not fly through space is to have some force here on the inside face. Okay. We said, oh, this is cool. This is how we ended up getting the shear stress. We talked about that in the past. And now we said that's really, really important when you start to work problems like this. And you probably thought you could forget about these, never have to deal with these problems. Maybe you don't even remember them. Or maybe you still wake up one night with a cold sweat on the back of your neck thinking of, two wood beams being hooked together with bolts. Okay? So hopefully it'll make a little more sense now. This nail is responsible for holding these two sections together, or transferring the interface shear, that's this, F, interface shear, between the top and the bottom plates. As always, this is not the whole story. This analysis assumes there's no slippage or no yielding at the interface. It assumes that none of these nails ever yield at all. It assumes that there's perfect contact. Everything is beautiful and wonderful. It's not that way in the real world. Now, these are really important. And the reason why they're really important is that if you don't have these nails in place, then your moment of inertia of your cross-section is not, you cannot use the ADY squared term. Probably never thought about that before. If these things are not hooked together, if there's not load transfer, then in a sense, you'd have to design them as two separate members. And you'd have to find the I of the top, 1/12 BH cubed, plus the I of the bottom, 1/12 BH cubed. But you do not get to use the ADY squared term if they are not hooked together. The parallel axis theorem does not apply. They're not hooked together. This is the first time I've told you that. I'm going to tell it to you 2 more times. Watch out for it. Okay, so there are 3 types of composite action that we're going to talk about. 3 different types. Okay? Where did I bring my notes with me? 3 types. And the first one is the one that you've been the fairy tale, the mythical unicorn that you've been calling and using for so long, called full composite. And sadly, we're going to still use it today because people can't argue on this partially composite we're going to talk about coming up. But in this full composite section, we have and for this class, we'll be talking about a concrete deck on top, or a concrete topping. We're going to be talking about a steel beam. Does not have to be concrete and steel. It could be 2 steel plates. It could be a wood plate. It could be plastic. I'm not sure why anyone would ever do that, but it could be. But we're going to be talking primarily about concrete and steel. And in full composite, you assume, or you have to have, no slip between the beam and slab. The good thing about this is that all strength of materials assumptions hold, and that makes everyone feel nice inside. And they have things what I mean by this is this interface shear is equal to VQ over I. Again, that's this stress. And if you want to get this the true stress, you're probably talking about VQ over IB. When you talk about interface shear, you design for a VQ over I type thing. VQ over IB is just integrating over the depth. It's the only there's no difference. Okay, just multiplying by the depth. Okay, that's all you're doing into the page. Great. And the cool thing about this, we said we would talk about this again. This, if we want to find the I of everything, it's 1/12 B H cubed plus A dy squared of the beam plus 1/12 B H cubed plus A dy squared of the slab. This is the same thing you've been doing, the same thing we've been beating in your head for so long. Okay? Beautiful. And then we have this thing called non-composite. And with composite, you have to provide load transfer here. That's really important. You have to provide load transfer here. If you don't provide load transfer, if there's no studs there, okay? No Nelson studs, which we'll talk about coming up. There's no, basically material or connectors connecting these two together. If you don't have that, you have something called non-composite. And non-composite means there's full slip between the beam and slab. This is important. Each member resists bending as an independent element. So again, the I, what's the I going to be for this one? What? That's exactly right. 1/12 BH cubed of the beam plus 1/12 BH cubed of the slab, and there's no ADY squared term. Why? Because they're not hooked together. There's no load transfer. So when you're doing these problems, believe it or not, does this ever happen? Maybe you don't have enough experience to know. On these type problems, you'll have an my over I calculation for the slab. You'd have an my over I calculation for the girder, and they're not together. Well, I take that back. Yeah, they're not together. They're not together. The stresses are not together. The stresses are not calculated together. It's calculated separately. But now when you want to talk about deflection, so when you want to talk about deflection, you would use the I of the system. Okay? I of the system. Okay, and then we have this beautiful thing called partial composite. What do you think that means? Well, let's go back and review. We said full composite meant, what about slip? No slip. Non-composite meant, what about slip? Full slip. Partial composite means, what about slip? Partial slip. We'll call it limited slip. Limited slip occurs. And this is sometimes hard for people to get or to get comfortable with. But what you allow to happen is you allow localized yielding of connectors. So what do you think the I will be for this? It's a good way to look at it. I like that. I like that. I like how you're taking what you know and trying to think about the problem. I like that a lot. And I'm not saying that's a bad way to attack the problem. But let's bound the problem first. Okay? So what do you think about the I? Do you think it's going to be higher than this? Can't be. Think it's going to be lower than this? Can't be. It's got to be somewhere in the middle. That's really what you were saying, Jacob. Somewhere in the middle. So we know that I partial composite is greater than I non-composite, but less than I composite. Somewhere in the middle. And that's actually dead on right. What do you think about capacity? It's going to be the same thing. Full composite is here. Non-composite is here. Partial composite is somewhere in the middle. We're going to come back to this graph. Now it's time to do the physical prop. Okay, let's try this. So I'm going to need you to push the button for me. They work. We're going to hope they work. So we're going to take two beams. This beam has the top and the bottom glued together. Glued. This beam has the top and bottom not glued together. Okay? Remember doing this before? Let's do it again. We're going to take this one. What was this one? No glue. And you're going to push on the top for me. Push and hold. Keep pushing. Keep pushing. Keep pushing. Oh my gosh! Hold it. Okay, I'm going to put my finger here and finger here, and you can hopefully see, oh, it's so blurry. Now it's not. Yep, you can hopefully see that there is slip. Everyone see the slip? Slip that's occurred. Thank you. You remember that stiffness? Remember that? Push on this one. Oh, what? No slip? Is it stiffer?
Oh, yeah.
Much stiffer? Okay, thank you. Oh, where she yielded it. Did you see that? So, that was there a difference in stiffness? Which one was stiffer? 5. It is. So what was the moment of inertia? It's the 1/12 BH cubed at the bottom beam plus 1/12 BH cubed at the top beam plus 80y squared to the top beam plus 80y squared to the bottom beam. That's stiffness, right? I? Right? The bending? Which one was less stiff? And the I again was 1/12 BH cubed of this plus 1/12 BH cubed of this. That's it. Okay? Okay. Other people can work on this. Don't break them. Now, so we just showed you the one with the glue was this. The one without the glue was this. We felt the stiffnesses, or Jennifer did, and the rest of you are working on it. Felt the differences in the stiffness. Partial composite. How could we ever make a partial composite beam? Stiffeners or connections. Connections at the ends are a very, very good idea. Very good idea. And we'll talk about that in a second on why that is. Okay? But only at the ends. Maybe they're much more helpful at the ends than they are at the middle. And you know why? Because the shear diagram. The shear diagram is much higher at the ends than it is at the middle. The shear diagram is. So you would expect these forces to be much more higher at the end or at the middle, and guess what they are? Okay? So if you have a choice, if you ran out of shear connectors, okay, and you have a choice on where to put them at the end. Okay?
Would that just cause less slip?
It will. But less slip means more capacity. And less slip means more stiffness. Does that make sense? And is capacity a good thing? Yes, it is. Is stiffness a good thing? Yes, it is. Now, what you'll find, and we're not going to go through all these calculations in this class, and we're not going to do it because right now the code doesn't allow you to. So, and I'm not sure when they will allow you to. Okay, it may be 10 years before they get to it. There's some testing that needs to be done, and people just keep wanting to see more and more testing, and I'm not quite sure why. But to get this, to get no slip, none. You got to use a lot of connectors. You got to use a lot of glue. Okay, a lot. To get a partial slip, it's this in-betweener. It's this idea that, you know what, we actually don't need 3,000 connectors because no slip is extreme, right? No slip, that means no yielding. That's extreme. It's really extreme. What if we allowed a little bit of slip? Structural resiliency says that's okay. Says that that's a good thing. But they're still hung up on structural resiliency for this application. And the reason why is because they're concerned about fatigue. They're concerned that if you've ever seen the way a Nelson stud is attached to a beam, it's usually done with a gun. I'll bring in a movie of it. Okay, they bring it down, they push the button, and it's welded. It's flash welded down. That weld's not inspected. It's hard to know what's going on. You're counting on that connection for strength. And if that weld failed, then you wouldn't have the strength. Does that make sense to everybody? So what they do instead, because they don't know the answer, they just put in a ton of connectors. And we're going to be putting in a ton of connectors in this class. You might say, well, and really, it's one reason why people probably haven't fixed it in the code is because it's not that costly. Okay? It's not that costly. It's in the hundreds of dollars per girder. Okay? So they just don't worry about it. that make sense? We'll stop right there.